Student, welcome to the 6th class in nuclear physics. Today we are going to look at the nucleus, considering that it is a quantum system. And students, as we have already talked about the nucleus, that it is since it's very small, since we are dealing with very small distances, it is a quantum system. So considering it to be a quantum system, there are certain terms and certain quantum numbers associated with the nucleons inside the nucleus. So this comes under the heading quantum numbers for individual nucleons. For individual nucleons. Now, when I say quantum numbers, of course, we are very familiar with certain quantum numbers like the principal quantum number, the angular radial quantum number, the spin quantum number, and all these things which are associated with an atom. And considering that there are several similarities between an atom and a nucleus. See, in an atom we have a nucleus which is positively charged, and we have the electrons. So these electrons, they have got a principal quantum number, and all these quantum number that I have just mentioned, such as the radial quantum number, the orbital quantum number, the spin quantum number, and such things. Now the nucleus, now when I take this nucleus outside, this nucleus, although it seems to be quite different, there are some similarities too. And these similarities come into our view when we look at nuclear models, which we'll do in the next section. But first, before going to nuclear models, let us complete this first unit, which is general properties of the nucleus. So in this, under this general properties of the nucleus, we have quantum number of individual nucleons. So even though, when we see the models, we will find that there is something called the shell model. The shell model is that particular model which can explain many properties, many observations about the nucleus. So according to the shell model, inside the nucleus there are the nucleons, that is the protons and the neutrons, they move in shells. So you see, this is not the atom, this is the nucleus. So looking at this, this shell structure, it was natural to think that there must be some similarity between the nucleons inside the nucleus and the electrons in an atom. So that's why certain quantum numbers were adopted, such as the principal quantum number, which we generally denote as n. But then there is a difference between the principal quantum number used in atom and in nucleus, because you see what happens in an atom. In atom, we have this electron. We are talking about the principal quantum number of the electron. So this electron is bound to the nucleus by means of a Coulomb force, which is an inverse square force. So Coulomb force, we already know that this is inversely proportional to the distance, like this. So this is the Coulomb force, but no such thing happens inside the nucleus, because in nucleus we don't have any core out there. We have all the nucleons moving on their own in a collective force of all the nucleons. So, and that's why it's strange, because we are not not totally aware of what kind of force nuclear force is. So this cannot be applied to M, which was used in atomic physics. Then there is the radial orbital quantum number. So we have the orbital quantum number, which is denoted by L, and it is assumed that all nucleons will have a orbital quantum number because they move about in orbits. So we have an orbital quantum number. Then we also have a spin quantum number, the spin quantum number, that every particle, whether it's a neutron or a proton, will have a spin s. And the orbital quantum number is h cross into s plus 1, the whole to the power half, which is very similar to atomic physics. In atomic physics, this was the spin quantum number for the electron in its orbit. So this is not in its orbit, but it's, yes, in its with respect to the axis about which the electron spins. And then we also have quantum numbers such as the magnetic quantum number, magnetic spin quantum number. Actually this comes under this, and we know that for every value of s, we have twice s plus 1 states, such as what? Such as s minus 1, s minus 2 up to 1, and then 0, then minus 1, then minus 2 up to s minus, up to minus s minus 1. So this is twice s plus 1 values. So these are the values of the magnetic spin quantum number, and this obviously arises only when the magnetic field is under the action of magnetic field only. But then I forgot to mention, we also have a ML along with L, so which also have twice L plus 1 values, so which also varies in the same way as like this, as s minus 1. So we'll have L minus 1 up to, so it varies from L minus 1 to L plus 1. So students, these are the same as you studied in atomic physics. These are the quantum numbers associated with an electron. So even protons and neutrons have these kind of quantum numbers. Then obviously we have J. J is the total quantum number. So it's the total quantum number, and J is equal to L plus S, just as in the case of an electron revolving around the nucleus. So we have this, and but then I forgot to mention one thing. S, as we know, is the spin, and it can take only values half and minus half. for electrons. But then we will see that this will not always be the case for all kind of particles. We will see that S may have integral and half integral values for different particles. Then till now these things are very much known to us and we have worked with them in our atomic physics. Now let's move on to certain properties which are new to a nucleus, which are exclusively related to the nucleons in the nucleus. So we'll look at these properties. This is, I'll name this separately as A. So this is the isospin quantum number. The isospin quantum Now students, isospin quantum number essentially came from the concept that neutrons and protons are similar in most of the aspects. So as we have seen, a neutron breaks down to form a proton. In the case of this Yukawa's meson theory, we saw how a neutron breaks into a proton with the emission of a pion, or for protons again gets converted to neutron. There's an exchange of pions. So it is considered that neutrons and protons are equal in all respects except charge. Neutron has got a no charge and a proton has got a plus charge. So Heisenberg came up with the idea that neutrons and protons are different manifestations of the same particle, different manifestations of the same particle. So if they are different manifestation of the same particle, that means they must be different in some way, and that difference was told to be the isotopic spin, which later was known to be named as the isobaric spin or the isospin. Let me students, what are these? What is this? This is that particular characteristic or that particular quantum number that differentiates a proton from a neutron, and it was assumed that a proton has an isospin of +1 and a neutron has an isospin of, let me write it properly, neutron has an isospin of -1. So that is the idea of isospin quantum number, and we will definitely study more about isospin or isotopic spin quantum number after we study the nuclear models and we become more familiar with other aspects of the nucleus. So this is just an introduction of the term isotopic quantum number. So I'll stop the part A of my lecture here. Please be with me for part B.